I mean, if someone's not saying, just I like to have So you've already, I guess you've already. Yeah. I guess you probably said
Here we go. Last class we ended where I almost started a new example problem. So we're going to do that today. But before we get into that example problem, I want to do a little review because I know it has been a couple days. And as much as I would like to say you studied all Wednesday on this material, I know that that is highly unlikely because there's other things to focus on, such as the prerequisite quiz. So we have our acceleration vector. And if we looked at it in normal and tangential components, that would include a tangential acceleration in the t direction and a, well, let's call this a normal acceleration in the n direction. The acceleration in the t direction is parallel to velocity, which means that we can treat it as if it were rectilinear motion. Which was in section 2 of this chapter, I think. But everything that applies to rectilinear motion applies to this variable, because this variable does not care at all about the direction. It only cares that it is speed. That speed could be going in any direction, doesn't matter. Here with the normal, this is perpendicular to velocity. And this can also be seen as v squared over r. And we got the v squared over r from some nice derivations of that unit vector. And we didn't go into detail about that, but this is from derivations of that time derivative of the unit vector. And what we can relate this to is curvilinear motion. Where v is equal to rho omega or r omega, depending if you're at a perfect circle or not. Acceleration is equal to rho times alpha. And if we were to substitute velocity into this v squared over r, we get a familiar rho omega squared and r omega squared if it's a perfect circle. R is a perfect circle. Rho is if you have a curve, but the whole thing isn't a perfect circle. So there are two directions we can go with this acceleration. We can also consider what would happen if we treated these as just values in one component and another component. And if you like linear algebra and are very comfortable with linear algebra, you might think of this as rotation matrices, where you rotate the coordinate system and change it into another coordinate system. So you can change a normal and tangential coordinate system into an x and y coordinate system. Later in this class, we'll also see how we can deal with mass times acceleration. And if we do go into curvilinear components, then this would be more of like an alpha, but well, I'm going to do kind of a small example problem, but later on we'll get more into moments and what that would look like with these accelerations. And where we left off last time is working an example problem that incorporates some curvilinear motion, rectilinear motion, and we're given some velocities, and we're given some accelerations in the x and in the y direction. So combining all of these together. Hopefully that review helped. It can be helpful to write all of the equations down. So this would have like the s naught plus v naught t and the other three that you're deriving in your homework. Having all these equations on one page. You can also substitute theta in for s if you're dealing with angles rather than a linear. A lot of equations that we talked through briefly, but when you start using them, it can feel a little bit overwhelming. And I've mentioned this before, but this is material that is unusual, where the derivations and just kind of like following along, and yes, I understand this step to this step to this step to this step, but then doing a whole problem becomes very confusing. So doing the actual problem is more confusing than the derivation. Maybe that's just me. I've never actually talked to anyone. After we finish this chapter, you should let me know if that's the same for you. So on the example problem that we did not start last time, there is a rocket that has center of gravity along this curved path. It is accelerating at 20 feet per second squared to the right, horizontally. And it is also accelerating downwards, where because it's so high up, the acceleration due to gravity is 30 feet per second squared. The velocity is 12,000 miles for every hour. And this is at a 15-degree angle. Obviously, that is much greater than 15, but I tend to draw my angles a little bit larger than they need to be because I'm really bad handwriting, and more space makes it better. And you know, Wiley Plus, they always just threw their numbers in anyways. I like to make excuses, but if you would like, you can make that angle as long as it's in the correct quadrant. I think that's good enough. Other people would differ though. And there is a change in angle with respect to time. So we know that there has to be an omega, which is d theta dt. And our rho is here. Based off of this information, we need to find rho. We need to find the tangential acceleration. We need to find omega, which is the time derivative of theta. And we need to find a vector for acceleration in the normal and tangential components. Before we get into just writing out equations, let's further define what values we're given. On the problem statement, there was not an X and Y coordinate system drawn. We should go ahead and draw that because we are given values that are X and Y. If we're looking for the final result to be normal and tangential, we know that we have to do some kind of rotation matrix. You can either do it by doing the full rotation matrix or individual angles, either one. But we do know that we have to do some kind of rotation to match up these accelerations with the coordinate system that we want. Because that 20 feet per second squared and gravity, they are perpendicular for one another. And that's all we need. One of them might be negative when we rotate it, but they're perpendicular, and that's the only coordinate system that we really need. The second thing we can do is identify the normal direction and the tangential direction. Normal is always towards the center of the circle. We're told that there is a center point of the circle located somewhere to the left of our rocket. And tangential is always parallel to velocity. So we have that now. I am going to go ahead and define our acceleration vector that we're given in X and Y, so we can clear those off the page. Our X and Y in the X direction is positive 20, the Y direction, negative 30, 0 in the Z direction, feet per second squared. Now we have logged this information. To make things more clear on the page, I am going to erase this portion and this portion that they were given. Also, I think this is brown. I think I've used that color before thinking it was black. So these were given, but we're going to erase it just to make a little bit more clear. And we have our acceleration. It asks for this acceleration later, but I'm going to go ahead and calculate that now, because based on our map from before, we are given this and we are looking for rho. We have to have some kind of information about these individual components. Therefore, we know we're looking for AN to get rho. So I'm going to go ahead and rotate this XY acceleration to match the NT. And from there, we can use that V squared over rho. And rotating for AN, primarily looking at this 15 degrees, will be a 30 cosine of 15 minus 20 sine of 15. Does anyone want me to break that down further into where the rotation actually came from? Okay, I can do that. X, Y, that's what we're given. And what we want is a T that is 15 and an N from this direction. It is also 15 because both of these coordinate systems are orthogonal. They're both 90 degrees. A fun fact about nothing important in this class, but for my dissertation, I dealt a lot with a coordinate system that was not orthogonal. So this is actually nice. Why can't I get black? There we go. Okay. So there are instances where having a non-orthogonal coordinate system is actually beneficial. Just thankfully, we're not there right now. So you have this rotation. We're now just looking at the normal, which incorporates a gravity and a 20 feet per second squared. So for the 30 cosine 15, which 30 is gravity, that's right. Because we're really high up. So for that normal direction, we need to shift over the cosine of 30. So that would, why am I messed up? Oh goodness. I just thought of this backwards and now I'm losing it. Let's do tangent first. I always have easier time with the tangent side. Okay, so 30 sine of 15. We want this tangent side. So when we're looking at 30, we can consider it over here where that 30 is, and it's the sine of that 30. And then negative 20 cosine of 15. This 20 is the cosine. I'm having a really difficult time right now thinking of a way to explain this other than just do it. So what I'm going to do is send out like probably a little document that has some of these coordinate systems rotated. If you're having issues dealing with this rotation, you can also always deal with a rotation matrix of sine, cosine, cosine, negative sine, and in this way determine if you have positive vectors, which way it's rotated. Yes.
I was gonna ask where is positive on that coordinate system?
This one or this one?
The one with the N and T vectors.
This and this are positive, X and Y are positive. So for this rotation, you can think about it as like Y going to T and X going to N. If that was, I don't know why I'm having a hard time explaining this. Yeah, I'll put out a document and then maybe next class go into more detail. Yep. So kind of, except that,
Does it change once we rotate it?
yeah.
Is that what the negative, because it'll be going like down?
Mhm.
But in this direction that you go, it's two separate axes.
Right.
Yeah, so if you're looking at it like this.
More than 1 and 4, that's probably less.
Honestly, you're saying words. They're going into my head and they're just jingling around. This will not be on the quiz today, so don't worry about getting it today. This is a really important concept. I don't know why I'm not explaining it well. I do, because I haven't explained it like this in a while. I'm gonna make a document that kind of steps through in smaller detail how to get these rotations, because I have done that before. And then next class, I'll start with that. Start with these rotations, because this is not the only kind of rotation that we're going to do in this class. Yeah, let's just pretend this whole time didn't happen. But if you like linear algebra and you like to keep things more theoretical, using this rotation matrix is an easy and nice way to do that. It just multiplies right in. Okay, so our 30, we need to take the cosine 15 component of that. And then for 20, we need to take the sine 15 component of that. Yeah, I need to like make unit vectors and stuff. I'll do that next time. I don't want to spend more time doing that. Okay, so for part D, we're going to pretend that we totally understood how to do that. If you take anything from this, just remember that there's a rotation that has to be done if you want to go from one coordinate system to another. Now we're going to look at A of n and consider the v squared over rho. So our vector n and t for the tangential direction is 27.1. And for the normal direction, it is 23.8 feet per second squared. And then one thing to make note about this is some people draw it normal tangential, some people draw it tangential than normal. I'm not sure which way I prefer. I think I'm going to use the order that the textbook uses it. So this is true. I'm going to use the same order that the textbook uses it, because I feel like that's most consistent. So they do normal, tangential, and then 0. So for this, that's just how I have it. Yep, so normal, tangential, 0. So that's 23.8 feet per second squared and 27.1 feet per second squared. That's the nice thing about XYZ is it's alphabetical order. Yeah.
What's the purpose of the 0 in the normal tangential?
It is not needed right now. So you're correct in that there's no purpose. The purpose why I write it is because later on we're going to be doing cross products and dealing with things that use 3 dimensions, and you can't cross a 2 vector with another vector. You have to have that third. And then also when we get into 3 dimensions, it won't be as scary because we've already seen it there. Also, if you're trying to use some kind of like coding that uses vector math and you don't put a 0 there, it will give you an error. And when I started doing a lot of this with teaching, I was teaching a computer lab. So I just like to write it that way. So there's no purpose right now. I just do that. Okay, so we do have our normal tangential. Yeah, XYZ, it's alphabetical order. It's pretty easy. We need to take this normal now. AN 23.8 v squared over r. We are given that our velocity is 12,000 miles per hour. And to convert that, you will multiply that by 44 over 30. I'll provide you these conversions if I do ask for them. I try not to because that takes up time. But if on the exam I ask for a conversion like that, I'll provide it for you. If for some reason I don't provide it for you, that's something that you can easily ask me for. So now with our v squared over r and our 8n, where you can deal with some curvilinear motion and find rho that is equal to 13.01 e to the 6 feet. So quite large, but we would expect a large number with a rocket. Yes.
Hey, how can you use that velocity in the tangential direction?
Yes. With this derivation that we did for right here is on the assumption that the normal is perpendicular. So this equation is only true because the velocity is in the tangential direction. And it's working on a change in theta. So the original, before we did major substitutions, it was dealing with a change in theta. So we're calculating a nice change in theta. And if you change theta enough, you get a circle that can have rho. But it's annoying to deal with theta. So we converted it from a value of theta to a function of velocity and rho. So now we can have an equation that is a normal that is perpendicular to v squared over rho. Yeah. And that's a great question to ask if you're thinking more about it later. You can send me an email and we can meet up and chat about it. So this is true because it is normal. AN is perpendicular to V on purpose. Now we have part A. Part B was to find a tangential. We have already done that. And we found a tangential here. That's 27.1 feet per second squared. The last new thing that we need is part C, which asks for omega, which is d theta dt, or theta dot. Omega, we have our g, velocity, tangential direction, normal direction. Last time when I talked a few minutes about the theory of curvilinear motion, I'd mentioned that the velocity is equal to r omega or rho omega if you're not a perfect circle. This is an equation that you'll reference back to a lot. It's not standalone, but it kind of stands alone. It's one of those few transition equations from curvilinear motion to rectilinear motion. So remember this because it sneaks up on you when you're least expecting it. Right now, being one of those times that we're least expecting it. So we know velocity and we now know rho because we just solved for rho. The one thing in this equation that we don't know is velocity over is omega, because we know velocity and we know rho. So velocity being 12,000, yeah, 12,000, and then that conversion 44 over 30 divided by what we found to be our, I about called that density, rho, which is the radius of curvature. then we can calculate a value that is in radians per second. And this is going to be pretty small. 13.53 e to the -4 radians per second. So everything in, well, now I guess this is going to be backwards. So for normal, v squared over rho, and we also used v equals r omega. At, we were just happy to have it. Velocity was given to us, so that makes it pretty easy here. And then we converted from ax and ay. So there's our little map here. So first we got rho, and then we got omega. So we went down that curvilinear path. I was hoping to have time to do another example that was like a quick example, but I want to go ahead and get into polar coordinates. Is everyone good with this problem, other than that rotation that I'm going to send more information about? We've dealt with two coordinate systems now. One that is fixed by position of objects in space. Then we have the normal and tangential that is based on velocity. And even though the normal direction was originally derived from angles in that rotation, we deal with that using velocity and the radius of curvature. Polar coordinates are incredibly similar to normal and tangential with a few slight differences. Again, we care about the direction of velocity, but the direction of velocity has to do with the radius of curvature, and our acceleration is connected to the length of r. So positive r hat is going to be outwards, because if our radius of curvature is getting larger, then it will be going outwards. And then also for this radius of curvature, the theta hat is going to be like perpendicular to r, which is great. Now, if this radius of curvature is constant, what would end up happening is you would have a perfect circle, kind of like I have drawn here. Perfect circle. But if you can see that the velocity is not in the same direction of that theta or that r, and that's because it only relates to this at this instantaneous point in time. if you're traveling through time and theta is equal to constant, then all you get is a straight line because there's no change in direction. You're just getting bigger and bigger and bigger and bigger. So as you go through space, if you have a change in both, you're mixing a circle, a perfect circle, and you're mixing a straight line. So what you get is like this weird path. And because we have this weird path and we don't really care about the direction of velocity, then you get some interesting situations where we have our velocity here, a radius of curvature that is not directly into the circle. So r hat, therefore, our theta hat is not directly into the circle. So that's the biggest difference for normal and tangential, is for a normal tangential coordinate system, the tangent is always parallel to velocity. In a polar coordinate system, it really doesn't matter. You're orienting your radius and your theta about a separate point that makes the curve kind of happen. It is okay if right now this makes no sense to you. We're in a very theoretical world. We're going to get into some more practical applications. We only have a few more minutes before I want to pull the quiz out. So we'll definitely be getting started on this next problem. But don't worry right now if this is kind of abstract to you. There's a reason it's not like taught as frequently as X, Y, because it is more complicated. So let's, before we get into the derivations, let's look at an example problem and then we'll go back and do the derivations. Because doing the derivations to explain an equation that makes no sense isn't really helpful, I don't think. Maybe it is, I don't know. So there is this rod that has this pipe on it that slides up and down. Already, we're changing here because we definitely have a radius that changes with respect to time. And we can measure this angle theta and measure this r here. If this is our point O, let's consider what would happen if our theta has a function. So that's 0.2 t plus 0.02 t to the third. Our radius also changes as a function, 0.2 plus 0.04 t squared. And we'll analyze this at t equals to 3 seconds. So we'll see where this rod is in 3 seconds. So unlike before, where we had the time derivative of the unit vector, now we're actually just dealing with the angle instead of looking at the unit vector. So we're looking for is the magnitude, the velocity, and the acceleration of r and theta. So typically when I do derivatives, I'll write the whole derivative out so that you know what is under here. I am going to switch to the way that the book does it, where if it's a derivative, there's a dot on top of it. And I would imagine you've seen this before. I will only use this dot to indicate a derivative if it's a time derivative. So if it's a derivative that is an unusual, like d over d theta, d over dx, I will write that d over dx. So anytime I write this dot, know that this is a time derivative. So we need to find the values of each of these. Let's go ahead and start writing these out and getting their magnitudes. And then we can apply them in our system, because what ends up happening is this is not the full story because of the product rule. As you go through integrating and simplifying your simple, I say simple, R equals R ER, which is where we start. As you go through and you get R dot and a R double dot, a double dot is not helpful. As you go through and get these, the product rule expands much more. So instead of having 2 breakdowns for the spherical coordinate system or polar coordinate system that has like breaks down by 3. We do need these individual components, however, to calculate it. So when I calculate theta dot and I get a value for this, this is not my complete answer, because my complete answer has to involve all of the other parts of the problem as it's rotating around. If that makes no sense to you, that's okay. We're going to get into this, all the derivations for this in much more detail, but I want to introduce to you the idea that the polar coordinate system is based more on the change in R and change in theta than we've done before, and that the derivations are super expandy. We'll have plenty of time eventually talking about this system to where it'll become kind of normal to you. We're not going to use this one as much as the normal and tangential. So if you only have time to like perfect one, perfect the normal and tangential, because that one we'll be using every problem, it seems like. So we'll get to these other example problems in next class. There's 2 example problems for polar coordinate system, and then we'll do a little bit of 3D and then get into relative motion. But for today, we are taking a quiz.